in this lecture, this is basically medical image processing software for 3D printing. So, as we know that you have one route is you can do a modeling and you convert as STL file and you print it, or in medical applications you start with CT or a MRI or ultrasound or PET, any medical acquisition, data acquisition system. So then that is the start point. So then again, why you need a software for again this software is intermediate software again, like in the first lecture, so which we have seen there are some intermediate software. So the medical image processing software is also intermediate software, so which we need to convert your images which you have taken from the Professor Krishnanand was in the previous lecture. So he has mentioned how these CT images are acquired and then it got reconstructed. Probably there are two algorithms, he is saying some iterative or a back projection algorithm. So in this lecture what I am trying to do here is this medical image processing softwares. Before starting the software, a bit of introduction to medical additive manufacturing or medical 3D printing. So that is the title of the course. And the importance of medical AM in the present context and the steps in medical AM and some allied technologies in medicine. Not only 3D printing, you have technologies like virtual reality, you have a virtual surgery, right, robotic surgeries, reverse engineering is the another technology where oftenly you may use, where you doesn't have a software or a soft data, rather than you have a outer surface, you have a physical model rather than, and looking for the outer surface. Say for example, you have in dental applications, you might have taken a denture from the patient mouth, so where you doesn't have a CT or a MRI. So definitely you must have some 3D scanning system to capture the surface or to digitize your dentures into the CAD model. Once you will get a CAD model, and then you can use it for your either implantation or template or device. So you can use it once you convert that physical denture into a CAD model or a computer model or a soft data. So and then a medical image processing softwares, one is a famously mimic software, that is a proprietary software, it may be a bit costly software also, and you have even a open source software called Slice 3R. So it may be almost similar capabilities, and we are going to give a demo. So Manmadachari is ready to give a demo after this brief lecture. And finally, what are the benefits of this medical AM? So this is the content which I am going to talk maybe in 45 minutes or so. So then why our course, the title, why we are here? So that is the medical prototyping using 3D printing. And if you see the applications, so you have the first share is consumer product or consumer electronics, that is 21.8%. and you have a second share is motor vehicle 18.6, which is automobile and automotive together. And if you see the third place, that is medical and dental together, 16.4%. So that is our interest. So then why this is apt technology for medical? So why? Because it's the third share. So definitely there is something in it. Otherwise, so it may not be the third one. It may be in some other place. So can you say what are the reasons? Can you say some 2-3 reasons why this is so attractive in medical? Yeah, correct. So every person is a unique, definitely. So that is the first reason. So every patient is unique, and you take the patient, each patient, if you put up age, so your things will be getting changed. Maybe your bone get porous or osteoporosity, or so once you put up age, so you may not be looking younger, or your skin may be, all this stuff. So definitely within the same guy which has the same anatomy, so maybe if once you put up the age, so you can find a lot of changes, right? So definitely this is the technology. None other than this technology will give a customized solution, no doubt in it. So any other second reason?
Less material, more profit.
Accurate, we have to have a debate. Why? Because accuracy may be good in even in conventional machining. You may get good accuracy in conventional machining rather than 3D printing. So accuracy, but that accuracy may be sufficient. The orthopedic, one of the orthopedic is telling that, so even it may be 2 centimeter, or sometimes depends on where your region of interest. So accuracy may not be the criteria. That may be the, definitely that may be the driving force. One of the driving forces. We are not looking for a sub-micron level accuracy in case of medical, but you may require for automobile, aerospace and other space which you are working. But definitely medical is the area which you may not be looking such kind of tolerances. So definitely that may be one more reason. Yeah, maybe. Yes? Yeah, the planning can be done even with the machined components also, na? Any specific thing? So of course one thing is the complexity. Once you have a more complex, of course the anatomy is more complex than any product which you as an engineer, you can design a very complex designs, but anatomy is a God's design, right? So anatomy is a God's design, so it may be still complicated, and wherever you have a complexity, your 3D printing is, you can get a free of cost as a complexity. So the one reason why this is so attractive in medical is the complexity of the products or the implants or devices or templates or any assisting device or implantable or a prosthetic, all these are very complex. So then wherever you have a complexity, 3D printing is easily it will take. So that is another reason, right? So like that you have several reasons, but it may be the customization, complexity. These are the two reasons which it may be good in medical applications. And if you see the expectations versus time, hype cycle or this kind of thing, and if you put the medical applications, right, say, and the person using orthopedics, those are the guys, they have been using it. If you see this is almost slope of enlightenment, or it may be the plateau of productivity. It is it is almost reaching to the production level. So the reason is simple. it's a load bearing bone, basically bones and joints. So what you required is, so it's going to be the substitute for a bone or a joint, so hardly it may take the loads, right? So then these guys are the early users, and people have been using this orthopedic applications, this 3D printing in orthopedics is, you can find a good number of literature or good number of applications. And if you see the dental is almost at the peak of, it is almost at the peak. So dental is another area where you can use slowly. It may be in the over period of 10 years it may go up to here and it will come here. And if you see the bioprinting, so which we are talking about, almost like, so can you print an organ, or can you print organs? Means like, yes, you can print some simple organs or tissues, like say you can print a blood vessel, you can print a bladder, you can print skin. Those are simple organs. But if you talk about heart, liver, definitely it has to go a long way. Why? Because that is what it is. We are at the triggered stage, in the technology at the triggered stage, and of course the medical research. And this is the dental means it includes oral maxillofacial, and of course if you put it oral, if you put it even cranium, craniofacial, maybe in between this or maybe here. But these guys, people have been using it. You have a tons of literature related to orthopedic applications. And briefly, if you put it, what are the activities, or in total medical AM? So of course this procedure, what is the start point? The start point is a patient data acquisition. So either you collect the patient data, you have several methods, either it is a CT, MRI, PET, or ultrasound, or endoscopy, or say anything, but you digitize it and take it as STL file, right? That's what a 3D printer take, only STL file. It won't take a DICOM image, which is a neutral format in case of a CT, MRI, or any other medical image processing or data acquisition systems, which you have a DICOM is a neutral format, how you have a STL file. So the DICOM, you have to start with a medical scanning technology, working with any one of, again depends on if you are interested, your region of interest is a bone, probably you may go with the CT, and your region of interest may be the soft tissue, so you may, the radiologist may suggest you, or he may suggest you to undergo the appropriate, the scanning technology or the data acquisition system. So then you will be examined, and then you will be, you try to get a DICOM image from the radiologist, and you take that DICOM image, and then we need to process it. So why you want to process the DICOM image? So basically a DICOM image is a black and white. The Professor Krishnanand was explaining you that there are the Huntsfield numbers, or the bone density. Based on the bone density, you have the gradation in terms of Huntsfield number. So you have a bone, and again you have a cocktail bone or a spongy bone. You have a range of Huntsfield, and you have a water, or you have a blood, or you have a different tissues, and you have a different Huntsfield numbers, or the bone densities, or the gray values, or whatever you call it. And then you have to segregate them. Why you want to segregate? So again, if you take at a particular slice, so it consists of bone, it consists of soft tissues, it consists of liquids, or it consists of a different white matter or anything, but you may be interested at a particular point of time, maybe a tissue or some region of interest. So then you must have some medical image processing software to do that. So for the segregation. So then we need to segregate them. So then we need to have some kind of a medical image processing software. So you have a plenty of medical image processing softwares in the market. So you have a Mimix, you have a 3D Doctor, Vaxim, Slice3R is a open source software, but rest will be the proprietary softwares which you have to buy. And once you process that images and then you convert as a CAD model or a computer model, then the first application is, so just you want to visualize the anatomy, right? Nothing to do with anything, but just you want to analyze the anatomy, just you need to have a one computer model, so that's fine. Just it will give some idea to the radiologist or the surgeon, so which they can understand the problem of a particular patient and what happens, maybe bone got fractured or some problem in the soft tissues. So definitely that will be the first level of application where you want to visualize in a 3-dimension rather than a 2-dimensional images which normally you get out of a CT or MRI, that too is a black and white images, but you want to enhance or supplement that images and reconstruct as a 3D model and give it in a different colors, and you want to have some rendered image. So then you have a virtual models, and then some extent a surgeon can manage to plan some surgery or to rehearsal a bit of rehearsal on the computer, but not the physical one. Maybe need not be every time a physical model, but maybe a virtual model is also sufficient. Like say if you want to do some finite element analysis, you have done some orthopedic or a joint you have designed, and you want to check whether the load is whatever the implant you have designed, whether it is taking the loads of a patient is self weight and other loads which it is falling on the knee or a hip or wherever it is, and you have a FEM analysis. If you want to do it, then the virtual model is sufficient to do FEM analysis. But we need to have something extra. So I need to have a physical bio model, and definitely you have to come with the 3D printing technology. So where you can, same thing, the computer or virtual model can be converted into a physical model. So definitely once you have a physical model, so you have a good number of advantages. So physical model is a physical model. You can have a touch and feel, which you never have a computer model. And again, there will be a limitations in the graphics and rendering speeds or so on and so forth. But a physical model is a physical model which you can have the surgeon's confidence levels is high. Why? Because he may be in the mindset that he has already touched the disease or a tumor or where he is going to operate. So he have such a kind of confidence levels, he already touched that part, right? So you have such a kind of advantage once you have a physical model with you, right? That's what then you, a next level of application, it may be a diagnostic model, just you can use that as a diagnostic model, or even you can pre-plan the surgery. So based on the patient biomodel, so you can pre-plan the surgery, even where you want to cut open, and then which part and how much there is a tumor, so and then how much portion we need to remove it, and all that thing, or what are the devices or the instruments you want to operate. So all the things you can very much plan before going to the operation theater, right? It should not be a guess game. So a doctor, a surgeon should not open the patient site and he should not look for where he has to operate, right? So definitely you have a surgeon will be having an opportunity where he can even pre-plan the surgery, right? And even he can customize the implants. So that is the advantage which people are talking about, the customization. Yes. So you can customize. It is not the standard size and shape implants. Normally they adapt either orthopedic or a oral maxillofacial or a craniofacial or any surgeon. Normally they may use some standard sizes and they are trying to fit it. But it never happens right? And sometimes they may use some, the fibula bone. No, it may not be 100% fitment, definitely. So then in that cases which you can customize the implant and you can customize the prosthesis, so where exact to the patient requirement, right, is a geometry and his anatomy, and there won't be any rejection or side effects, or there is no chance of failure of the surgery. Why? Because that data you have taken from the patient himself. And then that is about the models, right? And then you can make devices, the medical devices. So even that devices need not be every time implantable, right? But if it is an implantable kind of a device, then you have to follow a lot of regulations, whether it's a biocompatible, biodegradable, bioresorbious, then you have to talk about a lot of properties, but all the properties must be there in a single material. That is the challenge. But anyway, so that never happens, right? So how can you expect that biocompatibility, bioresorbability, bioabsorbability, all in a single material, right? So anyway, that's a challenging one. So then it can be implantable. Sometimes it need not be implantable. So just you may be using like a tools or the guides or the templates or the splints. So it's basically a tool which is assisting or which is guiding the surgeon to perform some surgery, right? So those are non-implantable kind of a stuff. And even you have some supporting devices, like you have some arm bases, or even you have some kind of a knee braces. This is all supporting devices and devices for elderly. So you all this stuff, so it is a support devices. So it can be a device, or even it can be anything, like it need not be every time as implant. So this is the broad spectrum of application. So again, what is your application, where the patient and which level of application you are using, targeting that 3D printed part. So then depends on, even you have some devices, so even you can make a device, so it can be a health monitoring device, or it can be any device, so which it can be helpful for the patient improvement. So then you have these kind of a stuff. And of course you have tissue engineering is another area where it's coming up. And organ printing, of course. So these are the two technologies or the two applications where it is relatively new, and there will be a lot of challenges. Why? Because when you talk about a tissue or organ, so and you exclude these two bottom two titles, and rest will be majoritarily it may be a load bearing, it's a bone replacement, majoritarily. But you talk about a tissue or organ, it has to do something else, right? So it has to function like an organ, which it's going to be printed, and it's going to be replaced, or it's going to be the repaired one. So there will be a lot of challenge. It's not that much easy. Why? Because it has to perform several things, not simply a load bearing, right? So this is a brief about the medical EAM. So what will be the spectrum, or like say, so once you 3D print, in how many ways you are going to use it, and where to start and where to stop, right? And then we'll come to the first step. So then you can have first any medical 3D printing application. Anyway, you have to start with data, acquiring the data either in terms of CT or MRI or a contact type, anything. And then as we discussed, so then we need to process the data. So then we need to process them, and we need to identify the region of interest, right? And then we need to convert it as STL file there itself in the data processing software. And then you identify, and you are in a position, what is your application, right? Say if you are looking for a splint, so then it should be very transparent, right? So then go with a SLA. SLA will give more transparent polymers among all these 3D technologies, 3D printing technologies. So depends, like say what is your application. So you are going to implant, so then implant that is in metal, then you have to look for a powder bed system, and it may be in titanium or cobalt chrome or a steel, stainless steel. So then you have to have a metal 3D printer, or otherwise you have to go with one intermediate step, like you go with some investment casting, you make a wax pattern or a sacrificial pattern, and then go with one more step additional, that is investment casting, and get the metal part. So anyway, so what is your application? Then you choose the appropriate technology as for your requirement. So not only 3D printing, so you have other technologies. So you have a virtual reality where a doctor can do a virtual surgery, though he is doing a virtual surgery, but he can feel like it's real. Why? Because you have a 3D head mount device, or even you have a 3D glove, or you have all tactile sensors, and you have all that stuff, like how a person really interacting. So such a kind of immersive feel a surgeon can feel, where he can feel that he is doing a real surgery, though he is doing a virtual surgery. So then he may feel that, or you have such a kind of all senses, like how all the senses you will be putting in terms of sensors here. So you will create all the senses, that in a three-dimensional 3D effect. So definitely it's wonderful for the surgeon, either it is an ophthalmologist or any guy, so they want to do some kind of a surgery. So definitely it will enhance the virtual reality. So not only in engineering, so even it can be applicable for the medical space, where you can use this technology. So which will supplement the CAD system or a computer or virtual model. So which you will be creating, you are giving some life. Basically you create a solid the model or a CAD model. It's a static, though it is a 3D, but you are giving a life, or you have sensors, and you are creating all that senses in terms of sensors, and you are getting in a 3 dimension. It's wonderful for the surgeon. So where he can do a virtual surgery like this, or even you can use a reverse engineering technique. So a reverse engineering technique, as you know, that where you have a physical object is there, which there is no a soft copy, or there is no CAD model, or there is no soft data. Yeah, oftenly you talk about the prosthetics, definitely where you are looking some nose or ear or what you call limbs. All these you need to have an external surface or dentures, where you will be taking impression, mouth of the patient mouth, you will be taking the impression, where you doesn't have a soft copy. So definitely it is a denture which you will be taken impression from the mouth of a patient. So, and just you digitize it, so just you collect the cloud of points, and then further you approximate, or you create a surface patch. So then you can whatever the bridge or whatever the crowns, so then you can, that is the patient data, and then you can modify. So in the software and in the computer, so you can do a lot of customization for this patient, which very much you can do it, right? So this is the one wherever you have such a kind of applications like limbs or ear, nose, prosthetics, all these prosthetics, so which we need to have. The CT won't work there. Why? Because you are looking for the outer surface, but not the inner details, but you are looking for the outer surface, right? So then you must have a reverse engineering or a 3D scanner, so which we need to scan it. And then briefly, if you compare these two approaches, say one approach is through a CT or MRI scanner, and you have other approach is a reverse engineering or a touch probe or a laser scanning. So the process starts with the patient, or it can be a dry bone, or it can be a prototype. It's already, you have some physical dry bone or a prototype, then we need to start scanning it, or we need to start acquiring the data. So just you acquire the data. So either use scanner, if it is internal data, you go with the scanner, and you are looking for the outer surface, you come to this route, and either it is CT route or a 3D scanning route. And then if it is a CT, you will get images. It's a number of grayscale images. which you are going to get. If you take a skull, it may be around 300 or 400, or it again depends on what is the slice thickness and what is the slice interval, and which are used in a CT scanner. So it depends. So basically, those are the images. And then in case of reverse engineering, you are going to get a cloud of points. But whether it is a point cloud data or images, so let it be processed. So for processing that, you have some softwares. This side you need to have some medical image processing software, and this side you need to have some reverse engineering softwares. To name a few, maybe Geomagics, and you have a Mimic software here. So you have other softwares also. I am not a representative of any one of these software companies. So you have in the literature you can find a lot of softwares, or even you have the open source softwares also in this domain, so which you can download free of cost, and then you can start working it. So then once you use these softwares, and then you reconstruct, or you register the points, or you stack the images in order to, your ultimate aim is to get a three-dimensional model, right? It's not an image, or it's not a cloud of points. So your goal is to make a three-dimensional solid, or it's a surface model which you are looking at. So then that can be done with these softwares, and then ultimately either you are getting it as a STL file, which is again depends what is your application. You want to 3D print it, or you want to analyze it, you want to do some finite element analysis for load calculations, or we need to do some CFD analysis. So then you have to convert that as a IGS or a step or any other file format. So then depends on your application. You save that data either a VRML, STL, IGS, or DXF. So the application demands. So then you save that data in the appropriate file format. And then you finally, that should be a kind of a geometric modeling should be done, means ultimately you should end up with some CAD model, either surface model or solid model we have to end up with. So then that will be done with these modeling techniques, geometric modeling techniques. You have a BREP, or you have a CSG, or you have a cell decomposition, spatial enumeration. You have a plenty of algorithms or the procedures to which you can convert your point cloud data or your images into three-dimensional models. So you have such a kind of, either it's a NURBS based or B-spline based. So you have a plenty of methods to do that. So then once you make that CAD model, so then your application demands a physical model, then you convert as STL file and you print it. And once you print it, so you have plenty of applications, right? So you can just use as a biomodel, yes, so that can be a biomodel, or it can be a surgical aid tools like template or guide or a splint or something like that. So that is supporting device for during the surgery for the surgeon. So it can be a tool, or it can be an implant which is going to be there permanently. It can be a implantable or non-implantable, but it's a implantable, it will be there permanently inside. So then it can be an implant, or it can be a tissue engineering scaffold. So you can make a scaffold for a tissue engineering application, or you can make some surgical planning models or surgical simulation model on that. And this is the opportunity. A 3D printing technology is a very good tool for a surgeon. So he can come out with an innovative surgical procedure, rather than which then people, of course, their experience and their skill a matter earlier days, but now it's no more. Why? Because you have a technologies like this. So if you doesn't have these technologies, of course, it is the experience and the skill of a surgeon. So and one biggest problem here is each patient is a unique, each operation is unique. So you doesn't have a standards like which you have a standards for ASTM, ISO standards. So surgery never have a standards. Why? Because if it is a trauma, we don't know the physical accident or anything, how it's going to happen. It never be similar to two accidents similar, it never happen, right? And disease or a tumor, it never be same area or same region of interest, we don't know, right? So then definitely each one is an unique, right? So then you have to have a kind of innovative surgical procedure for every time. There is no standard procedure. Say if this is the disease and if this is the trauma, that is not the same operation which is you are going to operate it, right? So every time it is a unique and a new, so you have to come out with a innovative surgical procedure. That's wonderful if you could do it, right? So definitely this technology will allow you to come out with an innovative surgical procedure. So then either it can be a FEM, just you want to see how the joint is withstanding loads or not, right? So then you need to have some FEM or CFD, again depends, you want to know if it is a cardiac, so then you may require some kind of a CFD analysis, right? So it depends, like what is the region of interest and what kind of application you are looking at. You want to study the behavior of the fluid or a blood, so then you go with the CFD or bones, loads, deformations, stress, strain. Okay, anyway, you have these stuff, and even sometimes it can be a medical device. So the medical device, so which it can be a device, so that device can be a drug delivery device, or it can be any other device, so which it can be used for the patient improvement. So okay, you have a plenty of softwares and you have a plenty of virtual models, but still why we need to have a physical model? Definitely a physical model is a physical model, touch and feel, right? So definitely, so for example, you take this case, probably a minimum two to three different surgeons. Why? Because so you are operating at the zygomatic bone and orbital floor. Definitely you must call an ophthalmologist in this surgery. Otherwise, so if you are putting the eyeball not properly, so he may lose his vision. So you have to call an ophthalmologist and you have to have a oral maxillofacial surgeon, right? So like that, so once you have different people and see how beautifully you can communicate, right? So how beautifully you can, either it is a team of surgeons or the patient counseling or anything, right? Say how beautifully you can communicate among the team, across the different surgeons. So it's wonderful once you have a physical model. So the surgical team, which it will communicate, and it will sometimes you can educate the patient. Once you have a physical model and this is what, there is a tumor, or this is what something has happened, there is a disease and which we are going to operate, so you can educate them and to assist the surgeons with the for diagnosing or a surgical planning. So wonderful, which you can plan, or you can even do a kind of planning the surgery or rehearsal the surgery or simulation of the surgery. Finally, so the best surgery ever before or innovative surgical procedure, you may be end up with such a kind of opportunities there here once you have a physical model with you. So, and even it can be a kind of a customized prosthetics. So it can be a customized prosthetics, or it can be accurate placement of your implants once you have a physical model, and you can accurately place it, not a guess game or not like assumptions, no guess. It's 100% fit. And say how to make it, how to fabricate the biomodels or a physical models. So then how to fabricate? So again, you may be having a conventional way of doing it. You may have NC milling, or you may have a CNC machines to do that. But again, the problem here is the complexity. So the complexity, again, once you have a complex complexity is free of cost in additive manufacturing or 3D printing. Of course, so whatever maybe the limitations you talk about a conventional subtractive processes, so once the geometries are very complex, why? Because so you have a lot of undercuts, you have a lot of voids, and you have internal geometries like neurovascular canals. Why? Because as we already said, it's a God's design, so it's very complex design, so it's very tough to replicate until unless you have a technologies like this. So, and that too, how to fabricate it? Okay, you can visualize it, but how to fabricate it? At the end of the day, so you need to have a physical model or a physical anatomy of a patient. So definitely, so you have and the difficulty with the programming once it is a CNC or a NC. So we need to do a lot of stuff, a lot of programming, a lot of jigs, fixers, so tools. So, a lot of stuff we need to organize, we need to plan, and we need to do it. But here nothing will be there, just you have a CT, DICOM image, take it and make the part. The part may be either a brittle, or it can be a soft, or it can be a sterilizable. You have a different materials now, so either it can be a gamma kind of a sterilization, or it can be autoclave. So which you have some of the materials can hold high temperatures and high pressures, so which even you can go with autoclave kind of a sterilization. So that is wonderful once you come with the route of 3D printing, right? So which you may not be missing once you go with the traditional NC practice. Then you again the medical imaging, as we understood. See, X-ray you have only one cross section at a time, you doesn't have a soft copy. It is only a film, which every time we need to take a printout for each cross section on the film. So again, thanks to the computers, which you have a CT or you have a MRI. So again, you have a computer backup of these images, so which you can even work on these images as for your region of interest. So it's a wonderful, you have a memory, you have a computer, and you can manipulate the images, you can reconstruct the images, so which otherwise you cannot do it in X-ray. And okay, let's start with CT MRI scan, and then that is a 2D cross sections, and then you are going to supplement, or you are going to enhance the capabilities of black and white two-dimensional images into different regions of interest, and different organs, different tissues. You can give a different masks, different colors, you can easily distinguish, or so you can do a lot of stuff on these, and ultimately you can very much segregate say you have the ribs, those are the bones, and you have lungs, those are the soft matter, and you have a nerve, or you have a blood vessel, or you have a spine. So again, so which even you can segregate all this stuff, and you can give a beautiful representation. So not only representation, these are not a static models, it's a dynamic models, means you can do some simulation, or you can do a kind of animation, or you can do a kind of a rendering. So you can do a lot of stuff once you have this kind of a virtual model, rather than working with black and white images, right? So, and in a brief, the general procedure, of course, it has to start with the CT MRI, and then these black and white images, and you must have some 3D reconstruction softwares to reconstruct it and save it as STL file, and then this is the routine process. You slice the data and send it to the machine and get your biomodel. Either use it for any one of the applications which we stated earlier. So just what you need to have is just you ask your radiologist to get a DICOM image of the region of interest which a patient has undergone. So that is the input which you need. And I may be discussing a bit of Mimic software modules, but anyway, this lecture will be followed by some demo on the 3D Slice 3R. So that is open source software. So what I thought is, instead of giving a demo on the Mimic software, as anybody is using Mimic software, you have an official license? Just please raise the hand. Maybe very few, 1 or 2 or 3. So it's very costly software. So what I thought, earlier I thought of giving a mimic software demo, but if it is a open source software, so everybody can access. So that is the intention. So, but more or less the capabilities may be same. Maybe the Chari is ready to give a demonstration on that software. So basically, you may have in order to extract the money, you may have a different modules. No, I don't want. My intention is not to comment these vendors, but like if you want this capability, you buy this module. This is some X amount, and this module Y amount, and this module Z amount. But maybe they may be putting in a different space. So it may be a CAD, or it may be simulation, or it may be a computer model, or FEM model, or physical model, or design validation, or implant placement, or the fitment, or visualization, or measurements. You can do a lot of stuff, right? So, but otherwise you cannot do it on a black and white images. So you are giving a life to the black and white images in terms of this, and then you will be simulating it, or you will be doing a lot of stuff on those static black and white images rather than you have these colorful three-dimensional models. So anyway, you have the import module. As I said, it should be a DICOM image. So all these make machines which you have a version of a DICOM or a NEMA. This earlier there is a one NEMA standard, but no, now it's a DICOM. So every machine, new machines, so you have a DICOM compatibility. Just you save your images in a DICOM format, and then basic tool. I think you are going to explain some of the tools, but it is not possible to explain all the tools. Maybe we have to have one separate workshop for that. So, but anyway, so the basic tools which we have to start with some thresholding, or like say you want to segregate, I need only bones. So means you supply some Huntsville number. So I need only the tissues which is in this range. So then automatically it will give you a region of interest, or a tissue of interest, or an organ of interest. So then you can segregate those the region of interest. So you have the thresholding, or you have a region growing, so which we need to separate it. So you have the region growing, and sometimes we need to edit it. So you have some draw tools, erase tools, thresholding tools, and dynamic region growing is another option. And you have some morphological operations you can do on this, and you can do even a Boolean operations. So you can have a 3 Boolean operations. You can perform on these Boolean operations on these images, and then you can do some cavity filling. This is a base or a core tools which you have a mimics, or not only mimics. Any medical image processing software must have these basic tools. So to start with images, editing of the images, or giving different thresholding or a different Huntsville numbers in order to separate them and getting finally a region of interest. So, and then even sometimes we need to reslice it, or sometimes we need to render it. So you have some neurovascular kind of a stuff, and a cardiac wants to know. So then just you have plenty of stuff to do in it. Any medical image processing software I'm talking about. So, and then you have a measurements. You can, if you want to measure some distance, but even some of the CT images, maybe with some softwares now it may be possible, but you may have extra tools also here. So which even you can go with profile line or gray value measurement, and you can have a density measurements or labeling, reporting. You can have tools like for visualization and measuring tools, the basic tools. If you want to design some implant, so you want to measure, so what is the wall thickness of a blood vessel, say you want to know, right? So like that. So then we need to do a lot of measurements once you are working with some kind of implant design. And then STL plus module, of course, it will create interface to the 3D printing systems. So either you can save it as ASCII or a binary STL, a DXF, VRML, or point cloud data. So which we can creating a interface to the 3D printing 3D printer. So basically, any medical image processing software, what is the job of any medical image processing software is, it has to create some interface as for your application. If it is a 3D printed, it should be STL file, and if it is FEM, it should be IGS, and it may be something else, it may be STEP, or it may be something else. But the thing is here, you are creating an interface, these medical images to a particular application. So then that's what these modules is available. So you have some FEM module, so which you can do some kind of material assignment. So you can do remeshing, or you can do a kind of say softwares like ANSYS. It may not be having all the biomaterials or a natural tissues or a kind of data bank. It may not be having in ANSYS. Why? Because ANSYS intention is different. It's not a medical software. So it may be you have a material, standard materials. Yes, you have a material assignment in ANSYS, but you are looking for a medical kind of a related materials. So definitely they may be having some kind of data bank which you can even assign the different materials, but there won't be any processor here. Just it will create interface to other FEM softwares like Patron, Abacus, or ANSYS, or Fluent, or Nastron. So just it will create a door, or it will create an interface. So from medical images to softwares like this. And even you can import this data to any CAD system like Creo or a CATIA, so which you can import these images into your CAD software, or vice versa, from CAD software to the any medical image processing software. It can be done. And then simulation, of course. So you can do a virtual simulation. So before you design an implant or performing a surgery, so a surgeon can do a virtual surgery or a simulation of a particular anyway. Tomorrow we are going to have one cranio case by Fanindra. He is going to show you how to design the cranium implant in a Rhinoceros software. So it's not a very costly software, so it's reasonably a less cost software. And tomorrow we will see exactly the same cranium. He is going to show you how to design and how to fit a custom made cranio implant, facial implant. And then you have a RP slice module which it will create interface to, you have a software, the supports, different kinds of supports. So they have some patents or some kind of support types. And say if you put it, if you want to generate, or if you want to create, if you want to develop a medical procedure, or if you want to produce a medical model, of course, so you have a different people. So that's what so you cannot work isolatedly as an engineer, and a medical community, they cannot work isolatedly. So right, there must be some kind of networking or a collaboration, otherwise you cannot perform the task, right? So for that reason, you see the responsibilities right from the doctor, radiologist, and you have again a computer specialist, or you have a RP engineer. So different people has to play a different roles in order to get finally a kind of implant or a model, right? So you start with a radiologist or a doctor. So start with the doctor, sorry, and then he may refer to a radiologist. So for reading the reports, either a CT or a MRI or a PET, whatever, or ultrasound or endoscopy, any stuff. So which it should be done by the radiologist, and then you have a computer specialist, and again sit with the radiologist and do some kind of a reconstruction and make the RP model, and then these are the auxiliary processes, and these are the main processes, and these are the responsible persons. So like which we need to have a team of people should be involved in order to get a required output, right? So, and if you name a few applications which I quoted, so it can be anything like in a medical, right from the bone to the tissue or organ. So you have different applications, need not be specific to these areas. So, but a common areas or a common areas where you can use this probably the AM or a 3D printing technology. So it can be orthopedic, the total hip replacement, knee replacements are performing nowadays. You have plenty of case studies available, and you have a dental implants. So where you need to have some mass customized crowns or mass customized the bridges. So you have a good potential to start some kind of a business in that area, or some orthodontic clips, or you have some kind of teeth aligners. So you have plenty of stuff to work on the dental, which you have seen in the hype cycle. So dental is at the hype, or at the peak. So you have a good potential. Somebody wants to have some kind of a business. So definitely dental is the area where you can think about it. And then cranioplasty, so which we can see there are some cranium cases which cranioplasty a bit challenging. Why? Because you have a brain, but no, I don't want to criticize. Orthopedic, it may not be that much challenge. So basically it's going to take the loads, right? It can be a joint, a knee joint or hip joint or shoulder joint. So basically you may be interested in analyzing the loads, but you have to do, your brain is there and a lot of nerves and other stuff. So then you have to be careful, and you have a cerebrospinal fluid. So then you have to be very careful once you are operating it. So then we are very cautious. We have done several cases with oral maxillofacial, but we never done any case with the craniofacial surgeon. We have done only modeling, analysis and simulation, but we never touch this part. But anyway, so this is the cranioplasty cases are there, and of course oral maxillofacial, there will be a plenty, tons of case studies in terms of oral maxillofacial and orthopedic cases. And then even it can be a biomedical devices. You can devise a customized device for a particular patient as per his requirement. So even it can be done, and it can be a biosensors, biomems devices, microfluidic devices, and even you can have some kind of a research models or educational model, anatomical models, right? So this is going to be a very good tool for a teaching aid. Even Chitra madam was mentioning, saying that she is using that guides, templates for even educating her BDS or MDS students, apart from using it in a surgical procedure. So it's a 3D printing is a very good tool and used as a teaching aid. And let me conclude my presentation with this slide, and then I will hand over it to the Manandachari to give a demo on Slice 3R, right? So that is an open source software. It may be having the capabilities of mimics, maybe similar capabilities or maybe less capabilities, of course. So, and before I hand over it to him, so just in order to summarize, so then what are the benefits you are going to get out of this medical AM or medical 3D printing domain? So what you are going to get it? So definitely you have a efficient surgery with reduced cost. Maybe cost in the sense, yeah, definitely it may be nowadays you have if you are using FDM technology for planning the surgery, rehearsal the surgery, so it may not be costing much. But if you are printing a metal implant which is going to be implantable, so it may be costing you much, but the outcome is good, but there won't be any complications, or the success rate of the surgery may be high. So, and then the operating room time got reduced, of course, no guess game or no imagination. So it's a straight to site or straight to region of interest, and then resect it and then do the job, and you can save a lot of operating time. Why? Because you already done some rehearsal on the biomodel of the patient. So then that is, you can save a tremendous operating time. At least from the literature, it may be even a 50% or 60%. Sometimes, some cases it may be more than that. So we can even get very good visualization or pre-surgical planning on these models, and of course it will improve the patient outcome. So you may be having a fewer complications and faster rehabilitation. That is another advantage you are going to get once you come this route, a 3D printed route, and it will increase the surgical precision to reduce the possibility of damaging to the healthy tissues. This is the important or underlying thing. So he or she should not damage the healthy tissues. So in spite of making the surgery or setting the things right, but one should not damage the healthy tissues, right? So then this may be the possibility of increasing the precision of the surgery without damaging the healthy tissues, and then possibility of performing a new previously impossible procedures or let me put it in an innovative surgical procedure. That's what I have been telling there. So somebody can have some kind of a innovative surgical procedure, it never done before, maybe possible. So, and better communication between the surgeons and the patient, of course, it's a touch and feel, or you have a kind of a physical model with you, and you have a precise design of the customized implants, and there will be a predictable surgical results with all these benefits. So definitely once you come the 3D printing, that's what the literature or the statistics are saying that. So this technology is a very good tool for a surgeon or a doctor or a radiologist. So for anybody in a medicine in general. So definitely you have a drug delivery systems, so what not, like say you have a pharma people can be used this technology. So then this applications to name a few, but it can be extended to any field or in the medicine in general, need not be a dental and medical, maybe in general in a medicine. So definitely this technology is going to revolutionized. Yeah. So this is my presentation. If you have some specific doubts, or I will hand over to, we have a limited time, like we have at 5:30 we have arranged the thing. I don't know how much time you are going to do, right? So yes. So Manmadachari is my PhD student, where myself and Professor Krishnanand, we guided together, and where he worked a lot. Actually, as you know that we are a faculty or we are the supervisors, just we will supervise, right? So the real work is going to be done by the student, a PhD scholar, right? Say, so I may be giving some presentations, but a guy who is behind this, or the people who works for this are directly with the doctors, or the personally with the softwares. So he has done a lot of work, and as I mentioned, like say you have and you talk about the steps involved in it. So right from the CT, so we have conducted some experiments on the CT parameters, like Professor Krishnanand also mentioned. So how a current or a tube voltage and the pitch will be affecting on the radiation dose, dimensional accuracy, or your volumetric errors, all this stuff, how it is, and how best we can optimize the parameters at the CT scanner level itself without giving a much dosage. And though you have a protocols for the CT MRI, so definitely you have a trade-off between your radiation dose and the accuracy. If you give more dose, you will get a clarity images. But the problem here is, you should not give a much dosage. So compromising, you need a better quality results, but you should not give no radiation dose to the patient. That is not ethically correct, right? So then without giving a much radiation dose, so how can you optimize the accuracy or the volumetric the volume, or rather than the volumetric errors in 3 dimension, how it is getting affected in the CT acquiring stage itself, and CT reconstruction, and even processing it in a medical image processing software, and further in the AM machine or any AM software, which we can further improve the parameters, and even after printing, so what kind of a post processing and how to sterilize them. You should not directly take these models into the operation theater and start working on it, right? So then you must have a kind of a thing, and he has done, and he himself and Santosh, Santosh is my the JRF, and which he joined in one of my DST projects, and they have done separate work, but basically they work on a oral maxillofacial cases on TMJ and some. So he worked with Chitra madam, and he worked with Aditya and other, which I have acknowledged in my book also. So if it is ready, I will hand over it to you. So he is going to give a demo on this open source software. That is what. So you can use this software once you go to your institutions, right? That is the intention.
I will teach. Good afternoon. Okay, this is the Slicer 3D software. This is a open source software you can get in the Google. Just a Slicer 3D. Then you can get this model. Okay, first you have to go for Dico images. Just here, this Dico image you have to die in the software. That's enough. First one. Now then click here OK, load the directory into the DICOM data. Now here the DICOM images are loading in the software, this 3D slicer software. Okay, when we are making the CT scanning, okay, first we are making the layer by layer. Okay, suppose if we want the head, it is taking at least 250 slices. Normally, the slice thickness having 0.625 mm slice thickness, minimum slice thickness. So suppose your head is the 15 centimeter, 15 and 150 mm divided by 0.625. How many slices are coming? That much images are saving in this DICOM file format. So you have to take the DICOMs from the radiologist and import in this one. Then click here OK. Now, okay, this is Gopi Krishna patient. Okay, now I am loading here. Okay, now you can see, okay, this is the different views. Okay, this is the top to bottom. Okay, exactly medical term, anterior to posterior. Okay, this is the front view to side view. This is the left to right. Okay, like that, whatever you are seeing. Okay, here you can see in the 3D CAD model here in this one. Okay, now we have to go for the here. So many modules are there in the software. These are all modules. In the each module you can do in the different work. But here first I am going to go for the volume rendering. First I am creating the volume. Actually the CT images are the totally voxels are there. That voxels you have to stitch in the 3-dimensionally. Each voxel having the XYZ coordinates. So you have to identify that XYZ coordinates and you have to together in the different voxels. Then you can make a 3D. That is the background, this one. Okay, just I am clicking here volume, just you can see. Next I am clicking here. Okay, this is the patient data. Okay, this is the virtual 3D-dimensional model. This is the 2D. Okay, here soft tissue is also there. Okay, here everything is taking the CT. You have to adjust the threshold values, whatever the Krishna sir is telling. Na? Okay, here we have to adjust the threshold. Here in the CT scan, Hounsfield units. Same as in the software, it is taking the threshold values. Okay, next. Okay, you can see here head. Okay, now go for the select. Okay, here in the different bone, okay, tissues you can taking. Suppose I am clicking here, you can see here CTA. Suppose here CT fat. Here the CT liver. In the different organs you can take. Which organ you have to take. That is, you have to click it. Here I am taking the CT bone. So now I am clicking a CT bone. Next here, okay, this is a CT bone. You can see here, this is not good. Here, this is the bone actually. This is the soft tissues. You have to eliminate the soft tissue by using the shift button. Just again, I am clicking here. So total soft tissue. Now you can see here how is moving. You have to play some game here. You have to adjust. In the mimic software, actually the threshold value you can set. Directly 226 values are there. Yeah, actually in the mimics that option is there, but in the 3D slicer that option is not there. You have to adjust by this cursor. That is a major drawback. But for that one, okay, so many projection algorithms are required. So CT, when we are clicking the CT, automatically some projection algorithms have to work. Like that, so many algorithms are required. So that's why, okay, here that algorithms are not there. That's why you have to arrange this cursor. But where you are using the mimics, that option is available. Yeah, according to bone, according to your tissue, directly some values are there. Suppose CT bone 226 threshold value you have to select, then it automatically bone only it will be take. But here that option is not there. You have to do some work. Otherwise you have to sit together, your doctor, and okay, both you have to adjust the value. He is a good person, he is the right person to take the decision. What is the soft tissue, what is the hard tissue? Okay, here you can see some bone also going outside. So some tissue is required. Okay, something is good. Okay, you have to play some game. Okay, you have some time is you have to take. Okay, now, so now you have to go for the clap. So here now, in this session, I am going to deliver how to convert the DICOM to STL. Okay, that's enough only. Okay, here, this is totally bony part. I don't want this totally bone. I want a small portion. How you have to take? That is I am telling you. Just you have to go the crap. And you have to highlight this one. Crap means already you know. Suppose you have to edit the picture. You are eliminating something. Same thing also, you have to crop all the images. You have to adjust. Okay, here, this is a boundary, this is a box. This box you have to adjust. The same this box you can adjust in the 3 direction, the 3 views, exactly speaking. Suppose I want to make this one, okay, directly you can assign here. Otherwise you can click here. Sorry. Like this one. Okay, when I am clicking here, you can see in the 3 dimension also it is changing. The different view have to adjust. Same thing here also. Exactly how to select this point and drag it by the mouse left button. Okay, like that some tools are there. Okay, now okay, this is the head. Okay, now you are selecting some volume. Adjust the volume by using something. Okay, I am taking only half of the portion, so I require only this much portion only. Okay, here I edited something. Now go for the crop. Here in the volume rendering module, just you are selected the volume only. Which volume you have to require. Now I want to go for the cropping of the images. So now you have to go for the different module in this one. So volume, sorry, all modules. Now crop volume. Okay, here this is my original one. This is the annotation ROI. ROI means region of interest. Which region you want? Okay. Before going to this one, turn off the ROI. Okay. 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 Now here scaling also you can adjust. Okay. Then click here apply. Now you can see these images are changing. Okay, now this is okay. Total full scale is there. Now I am selected some image. Okay, volume only. So remaining volume is removed. So that's why the images are adjusted. Whatever the three dimension is there. Next, go for the edit module. In the edit module, you can save it. Here in the different one, you have to do in the different volume or modules. In this 3D slicer, totally 84 modules are there. The 84 works you can do, 84 functions. Just I am telling only 3 functions only. Now go for the edit. Edit. Now it is asking you how to go for the edit. Yes, okay. Okay, now. Okay, here you have to go for the segmentation. Segmentation means it is connecting all the workers. Go for the segmentation. Okay, now in the segmentation, when I am clicking the segmentation, you can see everything is green. Here you have to once again you have to adjust. Here also. When I am clicking here, just observe the green lines. Okay, exactly speaking, this is a thresholding. This is exactly the density is selecting. Okay, normal term means. Then here click apply. Okay, once again go for the make model effect. This is a make model effect. Okay, then okay, what you are did in the thresholding, that is taking as a model. Then click here make model effect and click here what do you want here. I require the bone. Okay, bone model effect is over. Then apply. So whatever. Save. Okay, last one, STL. JPG. Here, okay, in this module, STL is not there maybe. Something here you have to select the STL. Just I will click one thing. Okay, something. Okay, here STL is coming. Just change the select the directory. Just I'm taking the documents. Choose, then save. Bone, sir. Is there? CT bone. No, it is not taking, sir. Actually, in this one, something is not there. Okay, here is showing the STL. Then the STL file you have to choose and save. Then you can appear in this in your software. It's taking, saving some time taking. Then that is you can see in your desktop. So, okay. Yes, sir. Okay, sir. Okay, okay. Okay, here, here, all modules. You can see here the brain strip rotation and different modules are there. You can select the edit. Okay, here edit button is there now. You in the each slice you can go erase and you can draw something. You can do something like that. You can do in this one majorly. In the next the useful one. Extra skeleton. That means suppose you want to add some extra portion, extra bony portion. That is you can add in this module. Like that in the different modules, you can add some different features. Okay, here majorly, I explained here only volume rendering and this crop volume and edit. This only I taught you. Here so many options are there in the so many features also available in this 3D slicer. But here little bit, this is the not automatic. Okay, you have to do your own. But in the mimics, everything is automatic. Just when you are CT bone, automatically that value is taking. And you can see that one. But here you have to adjust the thresholding like that. But almost everything is same. Here also so many features are available in this software. Thank you.